Example 16 is as follows. Two unbiased tetrahedral dice with faces numbered 1, 2, 3 and 4 are tossed, and the number on which each lands is noted. The score is the sum of these two numbers. Find the probability that, firstly, the score is even given that at least one die lands on a 3. Okay, so how do we approach this problem? Well, first we have to define our two events. So let A be the event that the score is even, and let B be the event that one die lands on a 3. Then what the question is asking us to do is find the probability that the score is even given that at least one die lands on a 3. So how do we calculate this? Well, we know that this is the probability that the score is even and one die lands on a 3, divided by the probability that one die lands on a 3. So how do we calculate this? Well, the top line is going to be the probability that what happens? That we get either a 3 and a 1, or that we get a 3 and a 3, or that we get a 1 and a 3. There are no other ways that two four-sided dice can be thrown to give us an even sum with at least one 3. So this is the probability that the sum is even and there is at least one 3. To work out the bottom line, I could work out the probability that there is a 3, but in this case it's actually slightly easier to do 1 minus the probability that there are no 3s. So how do I work this out? Well, what's the probability that I roll a 3 and a 1? That is 1/4 to get a 3 times 1/4 to get a 1. Or, in a mutually exclusive setting, I've got a 1/4 probability to get a 3 on the first dice and a 1/4 probability of getting a 3 on the second dice. So this is the second case here. Or I could get a 1 on the first dice, and that happens 1/4 of the time, and I could get a 1 on the second dice, and these two dice of course are independent, so I can multiply them together. So this is the top line. This is my chance of getting, here is the chance of me getting 3-1, here is the chance of me getting 3-3, here is the chance of me getting 1-3. And I divide that by, what's the chance that I get no 3s? Well, it's 1, so 1 minus the chance of getting no 3s. Well, I've got 3 out of 4 chances on the first dice, and another 3 out of 4 chances on the second dice, and because they're independent, I can multiply them together. So when I do that, and I do all this multiplication, it comes out to be 3 divided by 7. There is, of course, another way to do this. So the question remains the same. Sorry, I missed a spot there. The question remains the same, but I'm going to work this out slightly differently. So I still have to work out the probability that the event is even given that there is at least one 3, and that's still the probability that the event is even and at least one 3 divided by the probability that there is at least one 3. However, this time, instead of working out the probabilities, I'm going to draw my table of possible outcomes. So if we look at the scores here the score would be 2, 3, 4, 5, and so on. So I'll leave you to fill this in. So after you've filled this in, what can you see? What is the chance that I have an even score and at least one of the dice lands on a 3? Well, I can have this one, or this one, right? So there are three possible outcomes. Divided by, what is the chance one dice lands on a 3? Well, we've got these ones or these ones. So in that case, we have 7 possible outcomes. So therefore, the probability is just going to be 3/7. Question 2 turns the probability around. What is the probability that at least one dice lands on a 3 given that the score is even? So this time we're asked to find the probability of B given A. Well, we still start out the same way. This is still going to be the probability of B given A divided by the probability of A, or rather we've flipped it around now. And that's going to be, my mistake, hold on, the probability of B and A. Divided by the probability of A. So what's the probability of B and A? Well, that means that I've got an even score and at least one dice lands on a 3. That means I'm looking at either 1, 3, or I'm looking at 3, 3, or I'm looking at 3, 1. What about the probability that the score is even? This is a little bit harder to do, but if you list it out, what can I do? I can have 1, 1, or I could have 1, 3, I could have 2, 2, I could have 2, 4, I could have 3, 1, I could have 3, 3, I could have 4, 2, or I could have 4, 4. So these are my possible outcomes down the bottom. So if we work these out, we learned from the last time that the top line is actually 3 over 16. The bottom line, if you work these out, it turns out to be 1/2. So our final answer is 3 over 8. Now again, there is another way that you could do this. So again, I've drawn out my table of possible outcomes, and now we only want to look at the possibilities where the sum is even, or where the score is even. So we highlight those. So that means that in total I have 1, 2, 3, 4, 5, 6, 7, 8 possibilities where the sum is even. That's my reduced sample space. Of these, 1, 2, 3 involve one of the die at least being a 3. So therefore my answer is 3 upon 8. Now in general, we've got a rule for relating P of A given B and P of B given A. And you can see the particular working for this example here, but the more general rule is this, and it's called Bayes' theorem. And it says that if you're given the probability of A given B, that's equal to the probability of B given A multiplied by the probability of A divided by the probability of B, so long as, of course, the probability of B is not 0. And so you can read up further on the website given below.